Good morning and welcome to today's webinar. My name is Aranza Zualan and I'm a member of the BuildUp editorial board. BuildUp is Europe's largest international portal for energy efficiency and renewable energy in buildings. It is a unique community that provides the opportunity to discuss, contribute, and collaborate with other experts in this field. BuildUp aims to bring together stakeholders working in the building and construction sector to reap the collective intelligence about energy reduction in buildings by encouraging knowledge exchange. Our editorial work is organized around the topic of the month, which allows us to dig deeper into specific themes. Each month, several items are produced by BuildUp, such as overview and technical articles and written interviews, but that's not all. BuildUp also offers the opportunity to host webinars on topics related to energy efficiency and renewable energy in buildings. More recently, BuildUp has opened its doors to distinguished experts in the field to share their knowledge in front of our cameras in our BuildUp Expert Talks. The BuildUp portal shares daily the most relevant events in the field, but we also participate actively in many European events around the year, such as EPB Center and RIVA conferences, Horizon 2020 Interreg and Cost Action events, Covenant of Mayor, and more, always with the aim of further disseminating the results and helping to create high-quality media content. The BuildUp portal is updated daily, reaching around 120 new items each month, including news, events, publications, articles, and video content. But BuildUp is not only us. BuildUp is a community, and we invite you to be part of it. By becoming a member, you can contribute by uploading your own content and promoting your news, events, case studies, reports, and more. By contributing content, BuildUp will help you to reach a broader audience through our online portal, our social media channels, and our monthly newsletter. Visit our brand new portal at buildup/app.ec.europa.eu to find out more. It's our new portal. It is today a pleasure for BuildUps to host today's webinar entitled Replicable Solutions for Sustainable Plus Energy Buildings, a comprehensive evaluation including energy performance, LCA, LCC, and new business models, brought to you by the Cultural E project, where the goal is to go a step beyond nearly zero energy buildings towards the future of plus energy buildings. Today's webinar will firstly present an overview of positive energy buildings and solution sets as developed within the Cultural E project. It will then cover 3 presentations on specific topics related to the theme, each with an interactive poll for the audience to participate in. In today's agenda, we will start with an overview on positive energy buildings and solution sets presented by Francesco Isaia, Postdoctoral Research at Eurac Research. This will be followed by a presentation on energy performance assessment and harmonized control strategies from Francesco Turrin, researcher at Eurac Research. Francesco will follow his presentation with the first poll in Slido. Immediately following the first poll, we will hear from Roberta Di Bari, research associate at University of Stuttgart, who will discuss environmental life cycle impact, LCA. Roberta will follow her presentation with the second Slido poll of the day. The third and final speaker will be Dr. Hermann Leis, research associate at SIZ Energieplus, who will discuss life cycle cost and have discussion on new business models. During the presentation, there will be the last poll of the day, also in Slido. To run the webinar, we will have a Q&A session moderated by BuildUp. We invite you and encourage the audience to send us questions through the GoToWebinar platform that can be answered during the Q&A session. Please specify which speaker your question is for, or if it's for all speakers. You will be able to find the webinar recording on the BuildUp portal and our YouTube channel in the coming days, together with the presentation slides. Now we will move directly to our first speakers, Francesco Isaia, postdoctoral researcher at Eurac Research. Francesco, the floor is yours.
Thank you. Hope you can hear me and see me well. And so thank you very much for the introduction. And thank you all for being here. It's a pleasure to have this webinar. So before starting, I would like to ask the audience if you could kindly tell us via chat where you're joining us from and what is your profession. This would be very interesting for us to understand what kind of audience likes this kind of content, and so to have a better idea for us who we are targeting, let's say, also with our studies. So while you type kindly, if you want in the chat this information, so where you're from and your profession, I would directly start with a brief overview on the project and on plus energy buildings, to then leave the floor to my colleagues on more technical, let's say, presentations. So my name again is Francesco Isaia. I'm a PhD postdoctoral researcher from Eurac, and today I'm going to introduce you on the topic of positive energy buildings as intended in the Culturally project and what we call the solution sets. So first of all, let me start with the project. So the Culturally project is a project based on finding climate and cultural based solutions for plus energy buildings. And so the main objective is that of finding modular and replicable, so you hear this word again, solutions for mainly residential plus energy buildings, taking into account climatic and also cultural differences in the European context, while engaging key players and stakeholders in the whole life cycle of the building. And if you are here, you might be interested in general on these topics, and you can see in this slide our website, so culturally.eu, and you can also subscribe to a biannual newsletter if you wish, in which we provide our latest news. In the website you also find our reports and the work we've done so far. So the first thing I would like to talk to you about is the very definition, let's say, of what a plus energy building is. And this definition was developed within the project, was one of the, let's say, starting point of the project. And you can see here, let's say, a diagram, a graph that you can also see in the website, in which we give a definition of what we intend by plus energy buildings. And apart the let's say, more traditional and more intuitive, let's say, definition of being a plus energy building as, intending it as an energy efficient building that produces more final energy that uses via locally available renewable sources over a time span of a year. So also the time span is an important thing. We tried also to include other aspects and factors. So for example, we specify that when we take into account the energy consumption, we include not only the operational energy, but also the user-related energy consumption, which is, very, very tricky to do in a way, and also the need to get to a plus energy building also by ensuring the lowest greenhouse gases emission possible, and a good dynamic matching between generation and load. So also the interaction between the building and the grid needs to be appropriate and balanced. And a very important point for us is the one you see right here, which is also, let's say, an added value that we want positive energy buildings to have, which is the one also to ensure the final user to have an accessible, comfortable, and healthy indoor environment. So also let's say the indoor environmental quality is a key aspect for us. And so reaching positive energy building, it's something that needs to be done, taking into account the energy, but also while having the best possible comfort condition within the environment. Moving forward, you will hear in the next presentations and in general in the project about the geoclusters. And what we mean by that is the, let's say, subdivision of the European Union area in these four, we call it geoclusters, because it's let's say, the division to simplify and to represent the entire territory, and not only according to the diversity of climatic conditions happening throughout Europe, but also taking into account cultural and social aspects. So you will see in the map that we highlighted Italy, France, Germany, and Norway. And the reason is also because we are developing demo cases, so building real buildings, let's say, as demos in those countries, and we use those countries as a representative of some, the most, let's say, representative geoclusters, as we called it in Europe. So you will see that Italy is representative of the Mediterranean geocluster, Germany of the continental one, France of the oceanic, and Norway of the subarctic. So keep in mind that this subdivision was done not only, again, keeping in mind the climatic aspects, but also the very different, the differences in cultural and social aspects and behaviors that people have throughout Europe. And another key factor, and you will also hear, hear these in next presentations, is the one related to the technologies we included. And afterwards, I will tell you more about what we intend by solution sets. But first, let me start with the technology developments. So, of course, to reach the positive energy building targets and to ensure high quality, indoor quality in the environment, we need to use some technological solution to heat up the environment, to cool it down, to provide ventilation, and so on. So we focused mainly on these 5 that you see here. So smart air movement, active window system, packaged heat pump, cloud-based house management system, and strategies also for building flexibility. I will go through them very quickly to give you an idea of what we mean by it. But as you see, it's very much intuitive. So by smarter movement, we intend the possibility of using technologies, simple technologies in a way, like ceiling fans, but in a smart way, so controlled by smart algorithms, by innovative algorithms, let's say, that are able to change the speed of these ceiling fans in a way that the user inside can be comfortable even at, let's say, higher cooling set points than the usual ones in if we consider a summer condition. So we ran some tests in our laboratories using mannequins, using real people, and of course also doing simulations. And there was clear evidence that there is the possibility of using these kind of technologies to really decrease the cooling need by having a higher acceptable, let's say, cooling set point. So this was let's say, one of our key technologies considered in the project. Another one is what we call the active window system. So in this slide, you see the one aspect of the active window system. So it is, of course, a window system that has enhanced possibilities. So in this case, you see the possibility to control the shading. So you see an external Venetian blind in this case, but it could be other things. And you see also that we developed control strategies and we optimize the thresholds in order to optimize the comfort condition, considering both visual and thermal comfort. And this was really helpful because by managing it in a smart way, it's possible to lower the consumption while ensuring good comfort conditions. But not only our active window system is able, let's say, to control solar gains, but we are also considering, you see here just a couple of configurations, but there are many other possibilities of configurations in which we take advantage of the cavity to preheat air or to provide fresh air within the indoor environment. So there are many configurations, and they also are let's say, possible thanks to different technologies. So passive ones like trickle vents or natural ventilation, or active ones like ventilation machines. And of course, this is very tricky to simulate and to know how this will behave. So what we have done is to actually build prototypes. So we right now have in our Eurac laboratories this prototype, which are installed, and we are testing them. We are measuring temperature and heat fluxes to understand the real performance of this kind of active window system in a real environment. So this was another of our key technologies to push a bit more the let's say, behavior of the windows. Then the third technology considered is the packaged heat pump. So this you might understand a bit more, it's more intuitive what it does. So it's a heat pump in a very compact manner that can serve a household and can provide domestic hot water, heating, cooling, ventilation. So it can take care of everything that is needed within a household and is packaged. So you can actually use one unit and install it in a single apartment or household. So it's a very, let's say, nice solution for a decentralized HVAC or let's say treatment of air and production of hot water. Apart from that, we maybe more intangible but very important, we also consider the cloud-based HMS, so house management system, and building flexibilities. So you can see, for example, in this part of the slide that cloud-based HMS is at the end is an house management system with enhanced capabilities. So being connected to the cloud, it's possible to have more information to be shared among the different technologies and also to retrieve information from the internet. Think only about, for example, weather forecast. So it can be a very powerful tool to better manage the building. And also on the right side, you see the building flexibility drawn as a scheme, so schematics in which we basically wanted to best manage the way in which the building uses energy throughout the day. Also knowing a bit what's going to happen in the near future in order to, by using its flexibility, to best exploit its own PV production and so the self-generated energy production. So these are the five, let's say, main key technological solutions we considered. And when we talk about solutions, that is no other than, let's say, a set of these technological solutions among and others, because these are the key ones in which we focused. But of course, then we also needed to take into account the other, let's say, solutions as the PV production itself, the thermal energy storage, the battery energy storage, the more traditional, let's say, HVAC system or mechanical ventilation. But you have to imagine that all our, let's say, key technological developments, plus all the other needed technological tools, let's say, to control our building, needed to behave in the best possible way. So each one has to have its own, let's say, controller and control strategy in a way that it works properly, but also to interact among each other and to communicate among each other in order to behave in an holistic way, let's say, in the best way possible. So that's why we talk about solution sets. So having a set of technological solutions that work together to provide the best possible comfort condition with the minimal energy consumption. And that's why also in the next presentation, Francesco Turrin is going to talk to you not only about the solution set and the simulation we have carried out to, let's say, foresee what can happen in these buildings, but also about harmonized control strategies. So control strategies that can have like all these technological solutions work in the best way possible all together. So I would like to close. So yes, just a brief reminder about the next presentation. So as I said, Francesco Turrin next is going to present you more in detail what we have done to like simulate the energy performance of some archetypes, but also how we developed harmonized control strategies to have all these technologies work together in the best possible ways. And as introduced before, afterwards you will also hear about LCA, LCC, and new business models. So I thank you all for the attention so far, and I will leave the floor to my colleague Francesco for his presentation. Thank you.
Thank you, Francesco, and good morning, everyone. My name is Francesco Turrin. I'm a researcher at the Institute for Renewable Energies of Eurac Research, and now I will give you a higher insight on the implementation of those solution sets in a simulation environment and the control strategies. So I don't have control of the presentation yet. Okay, now it's working. Yes, so for the simulation tool that we use is Transys 18. For those who don't know this software, it's a software developed by the University of Wisconsin, and that allows to perform detailed simulation on both the building side and the HVAC system side. So the simulation we performed had a time step of 5 minutes, but the results I'm going to present to you are either annual or hourly. Okay. In the project, we consider two reference buildings as building archetypes. So we have on one side the low-rise building, which is a building with 3 floors and a net area of about 650 square meters. While on the other hand, we have a high-rise building which has 7 floors and a net area of roughly 3,000 square meters. So to consider for different geocluster, what we did is to consider different thermal transmittance values for both external walls and the windows, and these coefficients are the one coming from the laws of the specific countries. The solution set I'm going to present to you, so the results you will see only represent this solution set, which is a centralized heat pump, air-to-water heat pump system with all the technologies already presented included in the simulation. So what we have is a centralized air-to-water heat pump that provides domestic hot water, space heating, and space cooling. And the heat pump is connected to either a thermal energy storage for domestic hot water or a smaller buffer for space heating and space cooling. As emission units, we consider fan coils, then we have ceiling fans for air movement, decentralized ventilation system, Venetian blinds as shading system, then we have the PV with its batteries. So this is what the P&ID looks like. So we have the heat pump, which feed both the thermal energy storage for domestic hot water and the buffer for space heating and space cooling. For what regards the domestic hot water distribution, we have a heat exchanger which allows to decouple the primary circuit from the secondary circuit, and this helps in reducing the risk of Legionella losses while keeping a temperature which is not that high in the thermal energy storage. While for the space heating and space cooling system, we only have technical water, so we don't see any heat exchanger, but what we have is a mixing valve which allows to define what is the distribution temperature that we have. For what regards other boundary conditions, we have the weather files, which were taken from Energieplus weather files for each reference climate. We had to define some set points for the different geocluster, and those parameters were provided us from the partners. While for what regards the internal gains, so for internal gains, I mean the consumption we have due to plug loads, lighting, and the occupancy profile, they were created according to stochastic profiles. Okay, so talking about the control strategy, what our goal was is first of all to find a way to harmonize different components. So meaning that each component, like the ventilation and ceiling fans and whatever, has its own control, which is included in the component itself. And all these different control strategies should be taken together to create a unique control strategy that works in every condition. Then, of course, we have to guarantee the thermal comfort and air pollutant comfort for the user. We should also be able to adapt to some variation imposed by the user. For example, what happens if a user wants to open a window? So how does the system react to this change in the boundaries? And then we also try to optimize the system performance and to try to shift the load in order to be sure that we were able to match renewable energy sources production and the consumption of the building. Okay, so as I was saying, we have different components within the system which have their own control strategy. So here you have two examples for the ventilation on the right side. and for the shading system on the left side. So what we can do is to implement a centralized controller that is taken on one side, all the information coming from different sensors, and on the other side, we have both the provided control signal and the feedback signal. So the controller should be able to combine what is on the sensor side and what is on the different component side and try to understand what is the best thing to do. The controller itself, it's nothing fancy. So we have a block-based controller, which has hysteresis, schemes, modulation, and finally control signal. So what happens is that once we have all the signals coming from the sensor and the different technologies, we can combine those with some threshold to define what is the actual status of the system. And by combining those hysteresis, it is possible to define different working schemes. For example, the heat pump should work to produce domestic hot water rather than space heating or space cooling. And this is not sufficient because we also need to modulate. So each component must modulate, like for example, the pumps, valves, and etc. So by combining the modulation with the schemes, we are able to define what is the control signal to provide to the component. And a further step that we did is that we tried to predict what is the electrical consumption and the electrical production of the building and the PV system for each day. And to do this, what we did, sorry, this is just an example of the different sensors that are taken into account. So we have some sensors regarding solar irradiance, occupancy, indoor and outdoor, both relative humidity and temperature, the concentration of CO2, the state of charge of the battery, PV production, and the opening sensor on the windows. So when we speak about harmonization, what we mean is that, as already said, we have to define what the system should do when something changes in the boundary condition. So for example, when the windows is opened, what we do is to reduce the set point of that room, and this way we are avoiding to waste energy. Something similar is done when the ceiling fans are activated, so meaning that we have a higher air movement, and so to grant the same thermal comfort, it is possible to increase a bit the set point, thus reducing the thermal energy provided by the heat pump system. Then, of course, the battery try to prioritize what is the direct use of electricity, meaning that if we have a load and we have PV production, we're not trying to store this energy, but we try to consume it directly. Then the set points of the heat pump can also be modified according to what is happening to the system, meaning that I already said that we had a mixing valve which regulates the temperature we are giving to the distribution. And so what we can do to optimize the system is to let the heat pump try to follow this set point in order that we don't have an excess of energy production or we are producing less energy that we need. And finally, what we can also do is to try to change the set points of both the thermal energy storage for domestic hot water and the indoor temperature according to what is happening on the PV production side. And this is meant to say, okay, like imagine that today I'm going to produce more energy than the energy that I'm consuming, but I know that next day I will produce less. So what I can do is to try to use this excess of energy today to reduce the energy consumed tomorrow. But to do so, what is needed is some thermal inertia. How can we thermal inertia achieve? either we increase the size of the thermal energy storage, or we should act on the thermal mass of the building itself. So for this control strategy, what we did is to try to understand if it is possible to define a correlation between the total electrical consumption of the building and the external temperature, which in this case it is correlated to the heating degrees day. So for each simulation, so for each geocluster and each climate, we run a simulation with a normal controller, and we try to understand what is this correlation, if there is one. And at the end, we can see from this graph, here you have the total electrical consumption during winter as a function of the heating degree day. And you can see there is a sort of path. So what we can do is to try to linearize this equation, not linearize the equation, but to define an equation that tries to understand what the consumption would be. And so we ended up with this equation. And the same thing can also be done with space cooling, but in this case you see a higher dispersion of the data, and this is because during summer operations, so when space cooling is needed, there is also a higher influence on what the solar gains are. But at the end, you can see here that we have both the simulated and predicted electrical consumption, and on overall the normalized root mean square error is about 10. It's about 10%. So the idea basically was that when, as already said, when we have an excess of energy production today, we can exploit this energy to we can store this energy to be used in the next day. The same thing is done for the electrical production. So here we have the electrical production of the PV as a function of the global horizontal radiation on the roof, and as you can imagine, it is basically a one-to-one relationship. And what we end up is something like this. So here you see the hourly profile of one simulation. It is the 15th of January for the climatic Mediterranean geocluster and LoRa's building. And here you have the two profiles with the advanced control, which is the blue line, and the orange one, which is the basic control. So just going through this, what you see here is basically the base load due to appliances and ventilation. Then here you have the start of the heating, because during night we have a lower set point than during day. So when there is the shift, we for sure have to use the heat pump to increase the temperature in the building. But then here you see the first difference. And the first difference is that the basic control has a peak in the morning, and this peak is for the production of domestic hot water, and the secondary peak on the evening. And this is also for domestic hot water preparation. While with the advanced control, what we are able to do is to combine these two peaks and have it in the middle of the day, when theoretically there is more PV available. So we are not consuming less energy, but we are consuming less energy taken from the grid. Going to the yearly results, here you can see what is the thermal demand of the building for domestic hot water, space heating, and space cooling for the different building archetypes and different geocluster. So the first thing that you can see is that, of course, for climates like the continental and the subarctic, the space heating demand is higher, while there is basically no space cooling demand. In any case, what is the higher consumption is due to space heating rather than space cooling, also in the Mediterranean geocluster, but this is because we consider a climate of the, let's say, center North Italy and not Sicily or something like that. But yeah, never mind. What you can also see from this table, which is the how many hours in a day we are in the operative range for both temperature and relative humidity. And what you can end up with is saying, okay, we are with this system, we are able to provide the correct temperature and correct humidity throughout the year. Another important thing to see is that if you compare the low-rise building with the high-rise building, you see a decrease of the energy consumption, and this is mainly because of the lower S over V ratio, so meaning less losses. Going through what are the electrical consumption that you see in this graph, again, you can see that the higher consumption are for the buildings which have a higher thermal demand. But what is really interesting to see here is that the consumption due to appliances, so the blue part of this pie chart, is always above 50%. And this is a load that we are not able to control, nor we are able to shift in time, because in our simulation, this was a fixed profile defined for each geocluster. And yeah, so from this, what we can actually work on is the consumption of the heat pump itself. So it's about between 20 and 30% of the overall consumption that we can work on. For what regards the high-rise building, we see more or less the same thing, but on overall, again, we have a lower consumption. Going to the yearly energy balance. So in this graph, you can see for each building archetype and geocluster, what is the consumed energy, imported non-renewable energy, and exported energy. While here you have the yearly values for the self-sufficiency and self-consumption. So on overall, what we can say is that the imported energy, and by imported energy, I mean energy taken from the grid, is always higher than the exported energy. This means that the size of the PV that we chosen is not sufficient to grant 100% of self-sufficiency of the building. However, if we only consider the non-renewable part of the imported energy, then of course we can see that in few cases, but in more than 50% of the cases, this energy is a plus energy building. But for the Mediterranean case, it is due to the energy production of the PV. While for the subarctic case, the fact is that non-renewable energy is really low, and this is really low because the energy mix we considered is basically almost 100% renewable. So basically, we have no fossil energy coming from the grid. So to conclude, what we can say that it is possible to reduce the total consumption of the building by implementing a control that harmonizes the different technologies, and that the thermal energy system proposed is able to provide the correct ranges of temperature, relative humidity, and air quality. For both continental and subarctic climates, basically we don't have any space cooling demand because the little demand that we have is covered by the air movement. So by using ceiling fan, it is possible to not include space cooling from the centralized system. In each application, most of the electrical consumption are due to plug loads, which are difficult to reduce or shift in time. So to further reduce the energy consumption, the user awareness is fundamental. The advanced control system, control strategy is able to shift the load by matching the energy production and energy consumption. But to do so, first of all, we need to increase the thermal inertia of the building. And in any case, we are not really able to reduce the total energy consumed. For the high-rise building, we have seen that we have a lower consumption. This is due to a lower S over V ratio. And with the considered PV, as I said, we are not able to cover the entire building load and consumption. So either we have to increase the size of the PV, but the problem of doing that is that we cannot shift what is the seasonal behavior. Like in northern climates, we have most of the consumption for space heating, so during winter, when we don't have so much sun. And it is not possible to shift the production of PV during the summer season in the winter season. And yeah, to reach the plus energy building goal, considering all the consumption, so also including ventilation and plug load, etc., we cannot compare with the total energy imported from the grid, but only with the non-renewable energy withdrawn. So thank you for your attention, and we can go through the first poll of discussion. Okay, here you can scan this QR code and go into Slido. Okay, first question. If you would have to build a new residential nearly zero energy building or plus energy building, will you invest money in for an advanced controller? If no specific, why? So here I mean, yeah, imagine you are building a new building and you have to go for a controller. Would you go to an advanced one, or you simply think that it is not necessary? So it seems like an anonymous reply. Okay, thank you for your answer. Second question, in your opinion, what can be done to increase user awareness about the correct energy use? So as I said, about half of the overall consumption is due to plug loads, lighting, and etc., which are basically defined by the user. So how the users, how and when the user decide to use energy for washing machine, dishing machine, and etc. So in your opinion, what could be a strategy to increase their awareness and say like, hey, now you're producing more energy, so maybe you can plug your load now and not in 2 hours when there will be no sun. So in your opinion, what can be done? Okay, thank you all for your answer. I don't see anyone else typing. So I think that we can go to the last question. Question number 3. In your opinion, which of the following research field needs the most development to achieve the goal of climate neutrality of buildings? So we can either have buildings envelope, external walls and windows, photovoltaic system coupled with batteries, other renewable energy sources, heat pump system for space heating, cooling, and domestic hot water, advanced control strategies, all of them, none of them. So here is mainly, in your opinion, where there is the largest margin to increase what we already have. Okay, I think that everyone replied, so thank you all, and that was it from my side, and I will leave the floor to Roberta Di Bari.
Hi, good morning, and thank you for being here. Today I will present during my presentation some outcomes of cultural E regarding the environmental life cycle assessment of plus energy houses, and even more specifically regarding the solution set that have been just discussed by Francesco. So there was the last question regarding climate neutrality, reducing the global warming, which is the current big and really relevant societal challenge and we know that according to the Paris Agreement we should reach this carbon neutrality by 2050, and therefore passive and zero energy buildings can offer in this context new perspective in this and in this sense the class energy buildings are a step forward in comparison with the net zero energy buildings. They are also able to decrease the personal energy consumption, but at the other hand, as we just have seen, there is an increased amount of materials or installation components. Finally, there is the increased amount of surfaces aimed to photovoltaics and also batteries and further control strategies, so other elements that are related to the installation components. Since we are adding new materials, new components, it's important also to trade off the trade-off this energy efficient solution with their environmental potential. And in this sense, it's important to use reliable tools, which for instance is the life cycle assessment for quantifying the life cycle environmental impact. In Cultural E, we developed an approach. We started by following the cultural activities, namely the development of the technology, of the key technologies of Cultural E, and by following this development and by collecting the experience of technology developers and also experience of building designers, we start with the LCA of technology, so from the bottom, from the lower level, and then we developed a parametric LCA for solution set, so the second level, and finally we carry out life cycle assessment on concrete, on actual buildings, on Cultural E demo cases, so a completed building LCA. Since we are carrying out 3 different LCA analysis, so technology, solution set, and lastly plus energy buildings, we have also different goals and scope of the analysis according to the framework of the life cycle assessment, so the ISO 14044. When we are looking to the Cultural E technologies, the goal of the analysis was, first of all, allowing a comparison of the newly developed technologies with traditional one, identifying improvement potential, and in this sense also providing feedbacks to developers in order to even more enhance the environmental performance, environmental profile of their own technologies. And looking to the results of the Cultural E technologies, this is the example of the Hero Finestra of the active window system. with regard to the active window system, we saw that the total environmental impact of the Eurofinestra was slightly higher in comparison with traditional. While, however, this element also includes some ventilation machine and shading system, which are of course adding material consumption and as a consequence also embodied impact. We are in this sense then also providing as a feedback to the developers, just looking for other options which have a lower impact for the ventilation machine and shading system. Now, going to the LCA of cultural solution set, which have been presented by Francesco previously. Here, the goal of the analysis was, first of all, setting up a parametric modeling for LCA analysis, which can be replicable also in the future, and assessing our case studies, so the environmental potential of the 8 total case studies, and explore also benefits and barrier to overcome in different climate and cultural contexts. Francesco showed present previously the 2 main archetypes, which are a low-rise building and a rise building, and for each of these has been designed a functional system, so a proper solution set. These 2 solution sets related to the 2 archetypes have been located in 4 different climate and cultural context. So the Mediterranean, the continental, the oceanic and subarctic climate and cultural context. And totally we collect 8 case studies. For the data collection, we collect the information regarding the solution set, starting from the building, the installation plannings, and this allows us to derive information regarding production stage of solution set, so module A1, A3, and end of life stage. In this regard, we included just the waste processing C3 modules, the disposal, and the benefit and loads behind the system boundaries, so the recycling or reuse and recovering potential, module D. And then we also assess the operational energy use, where here the information is coming from the building energy simulations. We assess all the solution set, looking at the surface, the net floor area of the 2 archetypes, and we divided also the total impact per year, where the lifespan duration of our analysis is 30 years, which can be also related to the life cycle of the whole installation components. After the 30 years, we assume that there is at least a whole full refurbishment or substitution of all the components that have been applied or have been designed for the solution set. The impact categories that we are showing here is just the global warming potential, but of course we are able also to derive other impact categories with other environmental indicators. The environmental information is coming from generic data sets. We use the OCOBAUDAT, the German database for construction sector, and in also product specific information, which is coming from the environmental product declarations. Looking at the impact assessment, the life cycle impact assessment of our 8 case studies, we carry out the parametric modeling. So we divide the component in power generator and thermal energy storage, distribution system, ventilation and air movement system, pipeworks and photovoltaics, together with batteries. This information has been specified for the low-rise building and the high-rise building. And after collecting this information, then we sum all the environmental impact, and this allows us to derive the embodied impacts. So the share related only to the production stage and end of life, so the so-called grey emissions. As we see here, there is a slightly higher impact when we are dividing the total impact per the square meter surface for the low-rise buildings. And this is because the net floor area of high-rise building is, of course, higher, and there is a higher possibility to distribute the total impact related to the centralized solution set. When we are looking, however, for the share of each component, then what is here interesting is to see is that almost 90% of the total embedded impact of solution set is coming from photovoltaics and batteries. And this highlights the importance, the relevance of or the potential of photovoltaics for plus energy plus or for solution sets that have been designed for plus energy buildings. When we are analyzing then the operational energy, the operational energy, so the operational emissions also as well, we collect the results coming from the building energy simulation, and we calculate the energy balance for the 8 case studies. In order to convert the energy balance in an emission, we look at the environmental profile of the national energy grid mix of Italy, Germany, France, and Norway, and this allows this conversion. As we see here in the graphics for the low-rise building, as also previously presented, there is the possibility of reaching a positive energy balance, and this leads us to negative balances in terms of CO2, since the energy balance and the LCA are working with different reference systems. When we are looking to the high-rise buildings, the positive energy balance is not always reached, or it's not easily reached, and in this sense probably it is due to the photovoltaic surface, which are not sufficient for covering the whole consumption, the energy consumption of the building, and this means also an increase in terms of operational emissions. Just focusing on the case studies that reach a positive balance, or that can be this sense seen as a plus energy building. Then we calculated also an environmental payback period. So when we have an initial environmental investment, and this is due to the installation component that we are using in our buildings, but on the other hand, we have also the possibility to pay back through negative emission the initial investment, so we can calculate this payback period time. This payback period time is being calculated based on a variable, so a dynamic electricity mix. We look at the European scenarios 2020 for European countries, and so we collected different environmental profiles over time for the 4 national contexts. And as we see here in these graphics, we can see that the Italian and German examples can reach environmental paybacks by 2050. So this is a good take-home message. So there is the possibility to pay back the initial environmental investment. On the other hand, when we are looking to the French or Norwegian demo cases, this show a slower trend, even if they reach a positive balance. This slower trend is mostly affected by the carbon intensity of the current national electricity generation. If we go back to the previous slides, and we see here the first table collecting the environmental profile of the national electricity mix, we can see here that France and Norway has a really low intensive in terms of CO2 and energy mix. We are aware that France has a nuclear baseline, while Norway is mostly Norway producing energy is mostly coming from hydropower, and these produce really low CO2 emissions. And in this sense, we can see that also the payback period time are really, or in a first instance, really affected by the current national electricity generation. When we are lastly carrying out the LCA for cultural demo cases, the approach is similar to the one that has been presented for the solution set. However, it is important to remind that the solution set that have been here analyzed have been developed in a really theoretical way, while for the demo cases we are really analyzing actual, so not fictive case studies that have been really located. For that there is a more comprehensive also data collection. We can assess after this data collection the environmental potential on the whole building level, and here also explore benefits in their home climate and cultural context. I won't go really in details on the LCA of the cultural ill demo cases, because this deserves, in my opinion, other opportunities for disseminating and presenting, and more space and time for more comprehensive and more clear presentation. But what I can show you here is just another idea of the payback time on the building level. Here I collected 3 different scenarios for Germany according to the DGNB reference and target values. DGNB is an environmental certification system for buildings in Germany, and the system it's also structured in such a way so in order for establishing a reference building, which is, let's say, business as usual building, so the list that is required in the current situation. And then there is the target building. For that there is an ambitious environmental potential and a really highly ambitious building, which is the DGNB Target Plus. When we are looking to the reference building, the payback periods is really far away, and this is also happening for the target building. In order to reduce the payback period time, or let's say still working on reasonable or closer deadlines or closer payback periods, we should look at target plus buildings. For that, there is the payback period by the year 2070. And this leads us also to the final conclusion of this presentation. We look at solution set and buildings, and we saw that there are different performance levels in different climate and cultural contexts, and these effects are related to the design choices, cultural and climate context, as well as the national energy generation. So when we are looking to the design choices, the photovoltaic modules are the main responsible of the total embodied impact. There is an increase of materials, and this increase of materials should be taken into account in a really aware manner. Then there is a building type that can also dictate the operational energy within the high-rise buildings. Other surfaces besides roofs needs to be spotted, aiming at the positive energy balance. When we are looking to the climate context and the cultural context, due to the lower temperature, but also the annual solar hills, the continental and subarctic area reach less energy credits, as also previously presented by Francesco. And the continental and subarctic area, on the other hand, when we are looking to the appliances, to the usage of appliances, as also a higher user-related energy consumption. But this topic should be looked at more in depth further. Finally, so last but not the least, one of the issues that have been analyzed, that have been investigated through these studies, is the effect of the natural energy generation. There is, in this sense, higher effectiveness of plus energy buildings, solution sets, in Italian and German context. So in context in which there is a carbon-intensive energy generation. All analysis and observation needs to be, of course, addressed on the building level, and we should also consider in the building healthy analysis the effect of the refurbishment of the building, which is happening after the 30 years lifespan durations. And this will be presented, of course, in the future results or in future outcomes of our research. And I would be glad to show you or to show you again the other outcomes of this research. And I thank you, everybody, for your attention. I think now we can start with the poll. And here, the first QR code. The question that I am asking you is, in your opinion, how many years can be deemed reasonable for plus energy houses environmental payback time? Since we saw in this presentation really high amounts or really long lifespan, so which can be deemed reasonable. So looking also in just making also the analogy with the cost, with the initial cost investment. So there are people that are considering 50 years, 60 years. Let's also think about it. A building is designed for 50-year service life. So going behind 50 years, it's already going behind the service life of the building that has been designed. And then there is also people that are estimating 15 years, so really short payback time, and there is also the middle 30 years. Of course, the less is better. Cool, so, okay, one more. Also remember, yeah, the 30 years that has been proposed here in this presentation is reasonable, but it's also compliant with the deadline, so with the Paris Agreement. When we are talking about 30 years, then we are looking at 2050. For a new building or a refurbishment project, maybe less. It depends on the refurbishment, because also the refurbishment can be carbon intensive. So really roughly most of the people are estimating from 10, 15 years up to 30 years. This is the average answer. And then also people that are realistic and say, of course, 30 years, it's not achievable. Given the current situation, so 50 years, it's actually achievable. So I think we collect a lot of answers. I'm happy for that. And let's go with the next question for today. So based on today's presentation outcomes and your national context, in this sense, it's also important the nation, the provenience of the audience. Would you consider plus energy houses as a valuable solution for improving electricity mix environmental profile? So it seems that most of the people that are answering coming from national contexts in which there is a really relevant amount of fossil fuel for the energy generation. So everyone sees here advantages in exploiting the potential of plus energy houses. So here I think there is an agreement, I will say, yeah, a full agreement on it. So now yes, last question is we saw also in this presentation the relevance of gray emissions, so embodied environmental impact, and are using any strategies for the reduction of embodied environmental impacts already during the planning phases, and if yes, which is your strategies? So we see that here someone is associating embodied impact to the analysis of the load-bearing elements. Let's also remember that load-bearing elements might be mostly on concrete, and concrete is most of the time one of the main responsible of the total building environmental impact. So it's really important to design load-bearing elements. I really agree on it. It's really important to design in a aware manner all the concrete load-bearing elements, but also looking at the facade, the envelope, which are also one of the major responsible of the total building embodied impact. And yes, in this sense, it's really important using or including integrating the life cycle environmental information coming from PEBs or environmental data sets already during the design stages. And LCA, providing, let's say, a process accompanying LCA, a design process accompanying LCAs is one, of course, of the main strategies that are now also currently investigated and are becoming even more and more required on the European context. And yeah, for design option, we can use together with indicators also benchmarks, of course. It's benchmarking, it's a good strategy that allows even in the early design stages the comparison between different options, alternatives, and then can also help the designers in choosing the best option. Correct orientation and materials. Also, it's so an aware selection of materials, proper design. Cool. So I'm happy that people are already addressing the next challenge, I will say, for the building and for the construction sector, which is, of course, the embodied environmental impact, the hardware consumption of resources, together, of course, with reducing the operational energy in the buildings, and further reducing the energy, the operational energy of buildings. And I thank you, everybody, and we can discuss further later in the question and answer sessions. Now I leave the floor to Hermann.
So thank you very much, Roberta. So I would also welcome everybody to the session today. First of all, I would like to introduce myself. My name is Mr. Hermann Leis, working at the SIZ Energieplus. This is the Stein-based Innovation Center, Energieplus, which is located in Stuttgart and Braunschweig in Germany. And we are working on plus energy buildings, of course. And we heard a lot about technical things and LCA, which concerns material and things like that. And I would like to introduce some findings about life cycle costs concerning the plus energy buildings, but also some ideas about business models to support plus energy building dissemination, which is also an important point in the project. So maybe I can continue. Yes, it works. Okay, first, a very short overview about the costs included in the life cycle cost analysis. Here we see overall cost structure where costs are of the whole building come from, and the life cycle cost is a part of it. So what we do not consider is the income of the owner. This is the rent, for example, and the non-construction costs, neither than the penalties, which are maybe some fees for building permit and so on. But what we consider is the maintenance, the operation, and the construction is the most important. And the next point is we have to define a horizon of time. Or it works too fast. So what I mentioned is that we consider the construction cost and also the cost of replacement, and due to the limited lifespan, the maintenance and service cost, of course, the energy cost, and in plus energy building cases, the revenues for the energy sales, which came mainly from photovoltaic electricity production. And the boundary conditions we have is in this case the same like in the LCA analysis, 30 years, and we have to set a discount rate for the life cycle cost analysis because it's the annuity principle. And we also have some factors influencing the total cost finally. This is the price increase rate, which is set in, which can be discussed, but we set the investment price increase to 1%, maintenance 0.5%, and energy cost we set to 2%. So, and then if we have a look at the results, we have a look to the total annual costs. This means that the total costs are discounted for 30 years, and we distinguish between the capital cost, maintenance cost, energy cost, and revenues. And here I will show you the initial investment cost between an exemplary reference building and a plus energy building. And here we see the reference building, the gray one, this is the building site and the building cost construction of the building, the envelope and so on. The red one is heating system, cooling system is not included, and we have some other building systems like electrical systems. Then we have planning costs and some uncertain costs, which is this yellow one. And the plus in energy building, if we have a reference like NZEP building, so the envelope is not so different, so the cost will be nearly the same. But the investment cost for heating system might be higher, and then there is an added cost for photovoltaics and battery. And so in total, the initial investment cost is higher than in a reference building. And also, I did not mention this, we have a house management system, which also causes some additional cost. So if I continue, and here maybe we see the same reference building and the plus energy building, and here we have the total annual cost, which is on the left column the capital cost, the green one the maintenance cost, and the yellow one are the energy cost. And the red one is the result of all. And in the plus energy building, we have an additional position. These are the revenues of the selling of the photovoltaic system, the electricity coming from the photovoltaic system. So here we can reduce the total annual cost due to this sold of energy. And if we have a deeper look, we see that this the energy cost has an influence on two things, on the energy costs in the 30 years, but also if we do not have to, if you have a self-use of energy, then we have less cost, and if we can sell energy, we have a benefit. And here in this context, we see that the sale of produced electricity is really crucial for getting a plus energy building more economical than another like a nearly zero energy building, for example, which is here the reference building. So now I try to switch direction to business models. So we see that the surplus of produced photovoltaic energy is the only direct marketable output of such a plus energy building. And what we also see, if we go back, is that it is difficult to reach such an economic benefit with a plus energy building because the initial investment is higher, and what we get from the photovoltaics is not that much at the moment. And from this, we can find some targets or resulting targets of this. First is to maximize the produced photovoltaic electricity. We should maximize the photovoltaic installations on the roof, especially because here is we can get most efficiency compared to facade photovoltaics. And then another target would be the marketing of the produced electricity. And the third point is that the marketing of produced electricity must be made as simple as possible. This is a bit difficult, but this is also very important in this context. So I would show you later on a business model for photovoltaic marketing and more detailed about this. But first of all, I would like to show you business models in the context of plus energy building. So the goal in the project goals are to support the dissemination of plus energy buildings. So this is, we can say it easily, but what does it mean? So we have a look to the target group. The target group here are building construction companies, which can be very different. And we should identify the barriers, maybe national regulations, and other reasons why plus energy buildings are not that disseminated at the moment. And we have another target focusing on the marketing of electricity, is that we should include, or we could include, neighborhoods in our business models. So to the target group in our Cultural E project, we have 4 countries, and we have 4 different types of owners of building constructing companies. So one, in the German case, it's a general contractor. He's building houses, and he's renting the houses, also selling some of them. And in France, we have Veloja, which is a provider of social housing, also renting all the houses, or not houses, the apartments. But they have a restricted market. So this is due to the social housing target. And we have Abitcop in Italy, which are constructing buildings, but they only selling buildings. And then in Norway, we have municipal housing companies, or it's not a company, it's the community itself, which is building the houses, and they are also renting the apartments, and they also have a limited market. So I don't go through all of this, but this shows that this is a bit very complicated to bring all those companies and business models in one thing. So it's different, and therefore I focus here now in the case of renting, not selling the apartments, but renting them, because it's very different. And to have a look on the existing business models, we developed I call it a column concept, where we have the existing business model from the company, which the skills they have, the property management, they know how marketing their buildings, renting, sometimes selling, planning, construction. This is the know-how of the company. And now the question is how to integrate other value propositions, so new services or value propositions coming from the plus energy building itself. So this can be different things like operation contracting, selling of photovoltaic, electricity to tenants, or others or maybe property management, if it's not yet included here. This we can realize due to the fact that we have the advanced house management system. And what happens if this business model will be increase? It's a adaptation, but it's also increase. So the company should add some value proposition to the business model, so to enlarge the business model and the know-how. And this means that the company should have additional skills in technical point, legal point, and commercial point of view to integrate this new service in their business model. So, and here the question rises up: is this company able to extend their skills? So how can they realize this? And the next question: if what happens if we add further new services to their existing business models? So this might be a really barrier to adapt the existing business model for plus energy building. Therefore, we thought another model. This is a partnership model, where we say we let the existing business model of the company like it is, but we combine it with other companies having working business models which provide this additional value proposition of the plus energy building. And in this context, we have then an extension of the business model based on a partnership between the construction company and another company, an additional company. So this, just a second, sorry, I should go back. With this system, we can add a lot of more new services to the whole marketing of plus energy building. So the marketing of plus energy building would be this, or maybe if we add all the new services, so we have all these value propositions as additional things to the existing business models from the companies. And with this, we are able to adapt or to support the plus energy house marketing. So now some words about what influences the business models. So of course, the fast changing economical boundaries, like price increase at the moment in the building sector, or price increase of the energy cost, and then also legal framework, because this is country specific and it's also very heterogeneous. And then the framework is changing. At the moment, energy communities can be established, and also the marketing of local generated electricity is changing in different countries. And this, on the one side, this has a strong influence on the business model setup, and on the other hand, it is not possible to develop a general business model. So the goal here, what we do in the project, is to develop basic ideas, and these ideas must be adapted to the country-specific situations. So next slide. Yeah, I would like to give you an idea of what additional services or value propositions we found out up to now. So one everybody is speaking of is that the tenants can have a benefit from the local photovoltaic production. Means that they should have a lower electricity cost. This can be an additional service. And then we have green power supply for the tenants, which might be interesting for them. We have the possibility to rent, to make a kind of flat rate renting fee, which includes heat and power. That was something we tested, or we have models here in Germany. and we have experience with that, then we can provide green energy, green electric vehicle charging with the local produced photovoltaic power. And what do we else have? We can, what was maybe addressing some with some points which were discussed before, that we can support the energy efficient use of the apartments by a feedback app. Because of the HMS system, we have the possibility to analyze the apartments and the behavior of the tenants, and then we can give them a support to reduce their energy consumption. Then we can support property management also by using the HMS services. And we can, if we have a plus energy building, we can supply heat or power for the neighborhood. And another point would be to indoor environment quality as an additional value controlled by the HMS system. Now, this can all be some additional value propositions for the tenants or for the company building the buildings. And here at the end, I would like to invite you to give ideas from your side. What else can be an additional possible service coming from plus energy buildings? So at the end, the poll, I will ask this question again, so you have some minutes to think about it. And I continue. Oh, no, we can do the poll directly now because the organizing team put it here directly. So then we should switch to the poll. Don't know the number. Ah, yeah, okay. Then let's go to the poll directly. So please, if you have possible or other additional services and other value propositions to increase the rentability. So I did some suggestions. Maybe you have other ideas. So at the moment, I think this takes some more time. The comfort as a service and improved indoor environment quality. This is a bit similar, and this is a good idea. So this can be, or this can be realized by the building itself, by the envelope, and also by the HMS system, and maybe also by some algorithms developed. Was also an idea to develop algorithms for the HMS system to guarantee this comfort. So next question would be a value proposition for which tenants are willing to pay. This is a bit tricky. So this you should think about what could be interesting to have additionally, like for the tenants like they have now, if they move to a plus energy building. So what do they expect, and for what might they be willing to pay more? So this focus also on services which are not thought of at the moment, but which could be interesting to include in plus energy building concepts, maybe also in house management system concepts. So extremely low bills, no need to take care of maintenance and suggestions for the correct operation. That's a good idea. So it makes the feedback app obsolete, because this could be the main goal, so that nobody has to care about the energy consumption. Load shifts in relation to energy prices, also possible, I think. Controlled ventilations in the air quality. Controlled ventilation system for indoor air quality improvement. Yeah, maybe this is a point we should point out in the marketing, because yes, it's included, and if people are willing to pay for that, we can include it in the marketing strategy. Drastic decrease in maintenance bills for the lifespan of the building. So if vehicle charging also possible to integrate. So in our concept it is integrated. I think in others also. So somebody is still typing, so we wait. Easy access to e-mobility. Yeah, this is also interesting, and concerning the architecture. Okay. Higher summer comfort. I think this is more important in the Mediterranean region than in the Norway, but it is a point, higher summer comfort, which can come from the plus energy building. Okay, I think we can close the question, go to the next one. So as I mentioned, the legal restrictions are different in each country, and then I would like to ask you if you have ideas how we can lower the legal restrictions, or which restrictions you think that are obstacles for marketing of plus energy buildings. improvement in the possibility of sharing energy production among neighbors. I think this is really a restriction we have in several countries, and it's not so easy. And here I think it's something where the local government has the possibility to change in the direction of plus energy building. Same goal is variable rates for energy fed into the grid. So if we can sell it to different prices depending on the need in the grid. Warum ist das? Tricky question. Yeah, tricky question, as there are some countries that continue to forbid full detached buildings from the grid. Yeah. So I think to detach fully the buildings from the grid is not the goal. So this is not the goal of the plus energy building to be completely independent. But this is a point. So here we do not have a benefit for the grid if we detach them. So dedicated legislation for energy performance contracting, yeah, maybe also would help. Yeah, I think it's very tricky, this question. So, somebody still typing? No, nothing new. So as we have only 8 minutes to continue, so I would like to close the session and to continue with the example photovoltaic marketing, where we will see some restrictions we thought about at the moment. I go back one slide to show you the problem. We have a look to the possibility for electricity marketing in France, Italy, and Germany. We have the blue one is the price if you buy electricity. The orange one is the generation cost of the electricity if you produce it on the plus energy building. And the gray one is what we get if we feed back into the grid the electricity. So we see here the red one is the profit we can get if we sell it to the grid. In France, maybe we have some profit. In Italy and Germany, we have a loss if we feed our produce electricity direct in the grid. And the green one is what we could get if we sell if we have the possibility to sell the complete produced electricity to the tenants, for example, so or to the neighbors. So this is a big difference here. So it is important that the selling to neighbors and tenants is crucial for the marketing. Here an example of how it could work in Germany. We have the current cost for the tenants, which is a certain amount. And if we have the building owner, so he gets a bit cheaper the electricity, and then he produces electricity on the photovoltaics. Maybe he get a direct surcharge from the government, maybe not. But if we put this together, the owner of the building gets a mixed price, which is it's mixing from this what he's buying and then what he's producing himself, and this is not sufficient for all times, so he should buy from outside. And then he have a billing and distribution cost, and then he might be he wants a margin for profit, and then he should be at least 10% cheaper, like the price the tenant can get from other providers. So as the owner of the building is then, in this case, he is the provider for electricity, the energy supplier for the tenants, and he's the only provider. So the tenant is buying only from the owner, and of course he has to calculate his mixed price and so on. And what the problem often is that if he is the energy supplier, so he has all rights but also all obligations towards the grid operator and the end consumer, like the big power supplier also have. So they have all invoicing, electricity labeling, registrations, notifications, work to do, like the big power supplier also have to do. And this is a barrier for some owners of the buildings to extend their business models, because here we need a lot of extra know-how, as I mentioned in the beginning, technical, commercial, and legal know-how to introduce or to bring this business model into the existing business model. So here we see that the marketing, if marketing of photovoltaic is simple and straightforward, so it would be possible for the integration into the business model which exists at the moment, and this would increase the rentability of the plus energy building. So if they can sell all the produced electricity to a good price to the tenants or the neighborhoods, it would be interesting for the company. And if it is complicated and has legal limitations or restrictions, then it would be important to have a partnership for the marketing, and the added value of the partner is for the partner and not directly for the building owner. So this is another point, that the construction company of the plus energy building does not get all the added value coming from the sold photovoltaic, because another partner is involved. And this is, I think this is the current situation in most countries, that it is difficult to sell photovoltaics electricity. And I would, the conclusion is that the government should make it easier and simpler to sell the electricity to the tenants, but also to the neighborhood. And this would make it more rentability, would increase the rentability of plus energy buildings, and would make the marketing of plus energy buildings more interesting. So that's what I would say in this context as an example. And now there might be a discussion. I'm not sure if it's...
Yes, I will take the floor. Thank you so much. Thank you to all. We will now move to our discussion session. It has taken too much, all the speakers, but yeah, we will launch some questions from the audience that can still send us some of them if you want. So for Francesco Isaia, we have two questions from the audience. Francesco, the grid balancing point is interesting. Can you tell us more about this and the power correction factor that you have proposed?
Okay, yes, I think they refer to the slide about positive energy buildings that I was talking about. The key factor for us is to keep a good balance between load and generation. And I think maybe Francesco Turrin explained a bit of that also in his presentation regarding control strategies. So what we've done is to try to imagine also control strategies which are able to foresee what's going, like the expected production of the day after, so that there can be action taken during the current day, let's say, in order to they make the most out of the PV production. And in this case, this was, let's say, an example to make the most out of what you produce and to have a better balance between generation and product and load, let's say. I don't know if I answered the question. I hope I did.
I think so. I also want you to answer one question to you from our side. You were asking where is our audience joining from and what kind of profiles. And today we have a very nice amount of countries joining. So Belgium, Greece, Italy, France, Ireland, Australia, Spain, Norway, Hungary, Germany, and Latvia. He has been with us, so very nice. And we have all kind of professions, from architect, senior researchers, PhD students. What is really interesting that they are getting in the mood. Many EU project participants, so mechanical engineers, students for European Public Affairs. It was very, very interesting to see that they are joining us, and lawyers. So very nice. I want to give you that information. We will send it, but it was very nice to see and want to answer your question. Other question for you is from audience is that could you specify the strategies for the building flexibility that you were proposing?
Yes, again, I think I'm sorry if I can sound I'm giving the same answers, but it's actually a bit of in the same topic as before. So building flexibility intended as the possibility to change, let's say, to shift some loads and to change the way in which the loads are done in the building in order to accomplish something. So in this case, for example, a better matching of load and generation. So a good dynamic matching between these two things. So again, it's a similar answer, but the point is, like, flexibility is enabling us to do this kind of matching.
Also, one of your colleagues from Culturally, she's dropping a question. She said, which other actions coming from the users, such as window opening, are you taking into account in the simulations? Or which other actions coming from users could be included in the simulations?
Yeah, so of course, the user interaction with the building is a very tricky thing. It's not easy to model. And so what we've done is to, as Francesco Turrin shown in his presentation, we have not hypothesized a single, let's say, behavior of users, which were the same in all the apartments, but we use a stochastic approach in which there were different behaviors and different behaviors. I also mean, for example, the mere presence of the people within the building. So the simple internal gains they produce and the way they utilize it. And this is also because, of course, there are users which maybe stay in their apartments mostly during the day, others which are out during the day and are in the apartment during the night. So using this stochastic approach, we were able to model, let's say, in average, we can be confident that in overall the building has a behavior which is more realistic, let's say, than doing a single hypothesis on a single way of using apartments. Of course, then the measurements and the real building behavior, it's another thing, but we all know about the so-called performance gap. But this was a mitigation action, let's say, to cover, to let's say, mitigate this performance gap.
Interesting. For Francesco Turrin, that I hope he continues doing with us, it was very interesting to see during your Slido how our audience consider the building envelope to be underdeveloped in comparison with other technologies. Francesco, I don't know if you continue to be there. Yes, hi. Yep. How is this issue addressed in Cultural E, if it is? And if you have arrived to the same conclusions as our audience?
Well, in our project, we had a fixed geometry, so we didn't play much with fancy things. what we did to address for different countries is basically to consider different stratigraphies for the external walls and windows. But maybe during the poll, I don't think that it was, I guess, mainly meant to be for the envelope itself, but maybe the integration of something in the building, like PV integrated building, which is something that we did because I didn't mention it during the presentation. But the building, the PV that we have is not only on the roof, but it's also integrated in the facade. And then there are other technologies that can be included, so to make the external walls like an active system itself. So it can perform ventilation, it can perform solar heating, integrating PV. So I guess that it was meant mainly this thing, that not rather in okay, just put a larger thickness of insulation layer, because this is, well, only depends on the cost and sort of balance.
From your presentation, what is the percentage of load that can be shifted per day?
So actually, if we compare the basic control with the advanced one, we reach about 5 to 10% during winter, because of course there is less sun, while in summer we went up to 35-40% also. Basically, we had only load between mid of the morning to the afternoon.
Thank you so much, Francesco. For Roberta, I will drop the question you dropped to our audience. How do you deal with supporting environmental awareness during building planning process? Very interesting question.
Yeah, it's actually the question that I also asked the audience, and now which are the strategies? Of course, the digitalization in the construction sector will be a key factor that will play a role in the integration of LCA lifecycle assessment analysis in design or in the planning stages. And in this sense, it's important really in developing tools that are able to integrate the environmental indicators and environmental life cycle information in the design and the planning tools that are actually used even in the early stages of the design, which are the most relevant, are really a key for improving the environmental profile of the buildings. It's important here exploiting and using in the future benchmarking, so benchmarks that are coming from the construction industry, integrated this value in the design stages in order to provide at least an idea to the designers which might be the total environmental profile of the building, and identifying the hotspots, so the elements that have the hugest environmental potential and improvement potential in this sense. And at the end, also, in my opinion, it's really important having or including also a top-down approach, especially in the early stages. It's important to set up a limit of environmental potential, which can be still allowed in the future, because energy consumption as well as resources consumption, it's really a factor that will be discussed in the future. CO2 emissions are just a consequence of the consumptions of materials and energy. So we should really set up limits that can be used in terms of material consumptions, and finding out at the end also trade-off between technical quality or minimal requirements in terms of technical quality, and ensuring also environmental quality, so a good environmental or sustainable environmental performance of the buildings. So I think it's important that maybe an effort from all the sides, from all the stakeholders, from governments, authorities, just setting up limits, and also designers, so including more aware design. And in this sense, it's also important having the support from digitalization and tools. And yeah, I hope this will happen in the last year, since the time it's running and global warming cannot be it's already out of control. So we should really following or setting up our pace in terms of CO2 emissions.
Absolutely. Well, I will say that during your presentation, the audience was crazy asking for the sample of the house and room simulation that you have used, but I know it's very difficult to do it right now. So I leave it there like a possibility for continue a relation with Build Up, so you can propose or write for us on that. So keep an eye. we will get to you. But for example, there's a moment where you identify innovative technologies, and our audience were saying, can you go deeper in which technologies are these that are referring to?
Yes, in Cultural Aid, we limited it to the key technologies that have been here developed, and these are the ones also presented by Francesco Isaia previously. So the Eurofinestra active window system. We also carried out the environmental, the healthy analysis of the PHPs of the packet heat pump system, and the Vortice smart ventilation system, and finally of the the Aerofinesse, and also the thermal storage that it's included in the packet heat pump but of course, we are also open with designers. When we are looking at the demo cases, the designers were sometimes pretty open to innovative solutions and that are just alternatives, options that are proposed at the moment in the construction sector. We, in this sense, either find out our models as a Department of Lifecycle Assessment at University of Stuttgart. We have also an agreement with Fraunhofer Institute for Building Physics, and we are able to exploit our own lifecycle models or softwares for finding out some models that can be really representative, or even model one specific product which requires an own lifecycle model and an own lifecycle impact assessments.
Thank you so much. In any case, for audience, the website of Cultural is very good, so please go on it, because there is a lot of information there. I mean, we consult it quite often. Thank you so much, Roberta. And last but not least, for Hermann, talking about business models, key, right, for the implementation of all our ideas on real. I know we need to talk about business, we need to talk about money. I was quite thrilled about your comparison of free market compared to restricted market, what is apparently quite different, right? What are the common indicators that you find in these markets that could bring them in common, so they could be replicable for other countries?
I think I don't get your question completely.
You compare the German market was, if I'm not wrong, open market, so it's a construction company, yeah. But all the rest, Italy, France, and Norway, were restricted markets with very restricted form of business. Yeah. Which common indicators you find for the comparison that is the first, and how it could be replicable? It's easier in free market, right?
It's easier in free market. So to make it replicable would mean we should. It's difficult to find so we have restrictions in the restricted market. That means the Velocia, for example, they cannot sell to a free so there is you know what I mean. So the social housing is limited, so not everybody can go there, so the price is less. So the company needs to realize buildings with less cost, at least with less total annual cost. And this, as I try to show you, is if they have a good possibility to sell the photovoltaic electricity, then they can make it economically profitable. This is one thing, and the other thing is maybe there are other points, other added values which we do not have defined completely at the moment. So, for example, higher comfort or things like that. So this is not countable in money at the moment. So there's another work group working on this in the Culture E project. And for Velocia, for example, the replicability could be, for example, the advanced house management system, which makes it easier to the building management, and this makes it also cheaper to run the buildings, and this makes it interesting to use the plus energy building. And we have the side effect that the house management building system helps to make it economically advantageous to use the plus energy building instead of another one. So these are difficult to find out what is the main thing. I hope I answered your question.
Yeah, it's a very tricky one. I know, because you know, I'm Spanish living in Belgium, so for example, the social housing is completely different in both countries. So I was quite amazed, and I will follow your ideas in the business management.
It's also a question of architecture. So the architecture itself has a big influence on the total
Absolutely.
cost. So here it's not only plus energy building or not plus energy building. So there are other effects influencing the rentability of buildings and also the business models, of course.
Absolutely. So we are 17 minutes past the date. A big thank you to all the speakers and also to the audience for attending today's webinar. A reminder that you will be able to find the recording of today's webinar on the Build Up portal and our YouTube channel in the coming days, together with the presentation slides. And please keep an eye for the upcoming Build Up webinars. We have many in the pipeline for the coming months, so be sure to check our events calendar for more information. We wish you a very pleasant week. Thank you and goodbye.